Weir and Orifice flow. Okay, here's our learning objectives. And this is a lesson 6. I think I lost track. I think it's 6. Identify weirs and Orifice. Describe some common instances of weirs and Orifice in highway drainage design and apply the respective equations. All right. So what we see down here is a broad-crested weir, and this may resemble something that you deal with routinely, perhaps. It's kind of flat on the top, has sloping sides on it, or maybe like cars driving over top. No? Okay, you never see it. Well, that's why we're paying particular attention to it, because it's your roadway with your embankments, right? And then this is an orifice, all right? So just some definition terms. Here's a broad-crested weir. Here's the head on the weir. So actually, the head should be measured up to the energy grade line. But we know, just very similar to the OG spillway that we looked at, we have what type of flow condition up here? We have subcritical deep flow, and we know that the velocity head is pretty low. So the difference between the hydraulic grade line and the energy grade line, we're supposed to measure to the energy grade line, but the difference is pretty small. So we usually just say measure to the water surface, and there will be a little bit of error, but it's not significant. All right, so the head is measured from the water surface. The head on the broad-crested weir is measured from the water surface to the top of the weir right here, and that's capital H. We also have a head with Orifice, or with an orifice, and that could be one of two values. If this is not submerged, if this orifice is not submerged, which means that there's a free jet on the downstream side shooting out, then the head is measured from the water surface to the center of your orifice, the center of area. If this is submerged, which means no free jet, your water surface is maybe like around here or somewhere, you measure the difference from the upstream water surface to the downstream water surface, and that's your delta H. Pretty straightforward. There are other types of weirs. There's a sharp-crested weir, and that means that the water down here springs free of the crest like this. Then you have your not sharp-crested weir, keeping things, the KISS principle, keep things simple, silly, right? So the not sharp-crested weir, you don't see this water surface springing free of the crest, it kind of like comes right down the side of it. The reason that matters is there will be a different weir coefficient between these two situations, a little bit. It'll be a little bit different. So the basic broad-crested weir equation is this. The flow over the weir equals a coefficient. We love coefficients. We have coefficients for everything. We have coefficients for the weir equations and the orifice equations. The coefficient of discharge times this distance L, or length, times the head to the 3/2 power. We know what H is for our weir. We can look up the coefficient of discharge. For a broad-crested weir that resembles your roadway, the coefficient of discharge is around 3.0, give or take a little bit. But you could look it up in a table, and it varies depending on whether this weir is unsubmerged or submerged, which means the water level is at least up here. So this would be a submerged weir condition here. If the water level's down here, that's unsubmerged, and so that coefficient of discharge will vary depending on submergence or non-submergence. But again, you look it up in a table. And then we have this length L. So what is this length L? So again, hydraulic engineers rely on intuition and thinking logically about things. So you have two basic options. The weir length could be this dimension, and flow is going this way. So the length could possibly be this, or it could possibly be this. This one. Right. If we vary this a little bit, it may change our coefficient of discharge a tiny bit, but it's really not going to have a large impact on Q. If we vary this way, so if we go from, if flow is going this direction, if I go from a 1 foot wide weir to a 1 mile wide weir, which one do you think is passing more flow? The one that's 1 mile wide. So this is the dimension that is critical. so it's perpendicular to the flow direction. Okay, and that's your distance L, your weir length. All right, the orifice equation, you get it pretty straightforward. Again, we talked about what delta H is, so you can figure that out. A is the area of the orifice. There will also be a coefficient of discharge for orifice, and it depends mostly on the shape and geometry of the orifice. And again, you look this up in a table. For a sharp-edged orifice like this, it's typically in the 0.6 to 0.7 range. And then the orifice equation is simply this. I was having trouble with the equation editor in PowerPoint. It kind of truncates the square root sign, but this should be like all the way over here. Does that make sense? Yeah. So all of this is under the square root sign. So it's the coefficient of discharge times the area of the orifice times the square root of 2. Gravitational acceleration is 32.2 times delta H. So again, very straightforward. All right. So why do we care? Let's take a look at some examples of the application of the Weir equation and the Orifice equation and stuff that you commonly encounter. So we see here we have a circular culvert. It looks like probably, I can't tell if it's concrete or if it's metal, I don't know. And it's in a head wall with see, I told you we're going to do short answers. With wing walls, one thing to note here, and we're going to talk about this tomorrow afternoon, what do you see here? Yeah, you see some, well, this is slope erosion, right? And it may be, it looks like it's starting to come from up here somewhere. So erosion points, we'll talk about the importance of looking for those when we have field scoping discussions tomorrow afternoon. When the flow depth is this, and again, I think Veronica is a better artist than she gives herself credit for, but I am not a great graphic artist. So if the flow depth is about here, this culvert is acting as a weir, right? It's a different kind of weir. It's not a broad-crested weir. It'd probably be more like that square-edged weir, or not sharp-crested weir, I would guess. But this culvert is now flowing as a weir as long as it's in a term we're going to talk about tomorrow morning. I'm going to hit you with culverts first thing. Get you while you're fresh. Inlet control. In inlet control condition, this culvert at this flow level is operating as a weir. As that flow level gets higher, it's now operating as an orifice. Exactly. And then as that flow, and there's a transition between weir flow and orifice. It doesn't happen automatically at a given point. There's a transition zone between weir flow and full orifice flow. And then once the water gets up here, guess what? I have orifice flow in the culvert, and I have weir flow over my, which is, because what type of flow condition do I have is that flow cascades over, goes through critical depth, supercritical, lots of erosive kinetic energy, and as it cascades down the other embankment, that's hungry, yummy water looking for some delicious soil to eat up, right? That's not a good thing. Okay. Here is a curve open inlet, right? And you see the structural support posts in the top slab. And fortunately, you don't see it reaching out to grab some kid who's playing with his little paper boat in the storm. Anybody? When the flow depth is this curve opening inlet is functioning as a, yes. And now it's functioning as an orifice. And again, there's a transition zone between. And when you look at your design charts, you can see for these curve open inlets, there's a portion, and especially for culverts too, there's a portion that kind of looks like a weir component, and then there's a portion that looks like an orifice component, and there's a transition zone. All right, here we have, and I think I heard someone mention this morning, here we have a culvert that functions as the principal outlet for a detention pond. And so when the flow level is there, it functions as a, and we can calculate how much discharge is going through there because we have the weir flow equation. When it's up there, it functions as an orifice. And when it gets up here to the emergency spillway, the principal spillway is acting as an orifice, and this riser here is functioning as a not sharp-crested weir. If you had maybe a corrugated metal pipe up here, maybe that would be a sharp-crested weir. And the coefficients of discharge are just changed a little bit, okay? As well as the length. So when you're looking at the length, put in the Weir equation here, what are you going to use?
Oh, the entire perimeter of the thing.
Okay. So again, that's that intuition coming into play. Right. Common weirs in highway drainage design. So curb opening inlets that we looked at. Grade inlets also function as weirs at lower flow, and after a certain level of submergence, they function as orifice. Detention basin outlets, culvert entrances when inlet controlled only, and flow over embankments. Those are just some examples, and you could probably think of another 5 or 10 examples to add on to that list. Common, that was for weirs, and then for orifices, flow through bridges when they're going into that pressure flow condition, right? Curb open inlets and sags, grates and sags, culverts when they're submerged, and inlet control.